Okay, we're doing lessons 86. 86 is a relatively short lesson. It's stuff that you're very familiar with. Something that'll just be a bit of a review for everybody, and then we'll jump into lesson 87. Lesson 86 is simply the number families. It's found on page 592 in your book. If you have your book, and you should, you can turn there and see. It's nothing you don't already know. It's stuff that we're just simply reviewing. Simple terms like what is a counting number, what is a whole number, what is an integer, and what's a rational number. So in your book we see starting off with counting numbers are simply that. They're numbers that we count when we normally count. You know, when we go and play hide and seek and it's your turn to count, you know, we cover our eyes and we start, okay, I'm counting to 25. 1, 2, 3. You know, we don't start at 0. You don't say 0, 1. You know, so that's 0 is not a counting number. 0 is a whole number. But when we're also counting, we don't say 1, 1 1/4, 1 1/2, 1 3/4. Sometimes parents do that when they give their kids till 3 to get over here. They don't get over at 2. They'll say 2, 2 1/2, 2, and you better hurry. You know, but typically it's not a counting number. You know, we just don't want to spank our kids or punish them, so we give them a chance to. Of course, I never did. I counted to 3 or 5 or whatever, and they didn't get their. They paid a price. Just the way it goes. Anyway, counting numbers are numbers you count, guys. 1, 2, 3, 4, 5. That kind of a thing. When we're illustrating these numbers on a number line, and we're at 0, that would not be a counting number. 1 is, 2 is, 3 is, and 4 is, and 5 is. We put a arrow, we make sure we have an arrow going that direction to say that these counting numbers go on forever. Notice I would not put an arrow to my left because counting numbers do not go in that direction. Okay. Also, if I were asked to and we're going to do this in a minute, so maybe I'm getting ahead of myself, but if I asked you to list all the counting numbers greater than 1, then you would not list 1 because 1 is not greater than 1, but you would put a dot over 2, a dot over 3, a dot over 4, and a dot over 5, and any other numbers that might be listed here. And that's showing that the counting numbers are 1, 2, 3, 4, and 5. The stuff in between, now there are numbers in between here, but they're not counting numbers. Okay? They're actually called rational numbers. They're ratio, and rational sounds like ratio numbers, like between, what's between 2 and 3? Well, maybe 2 1/2, right? Fraction, 2 1/2. Maybe 2 3/4. Maybe 2.1 or 2.2 or whatever. All those odd numbers are not counting numbers. So we can't do what we did before by put a dot here and go all the way over, because that was saying what numbers are greater than or equal to a number, and that would be all the numbers in between. But now when they ask for counting numbers, we're simply showing the counting numbers by putting a dot on top of the actual counting number. Everybody got that? All right. Whole numbers are the same way. We use dots to represent what they are, but we include 0 as a whole number because 0 in fact is a whole number. It's not a counting number. We don't use it when we're counting, so it's not a counting number, but it in fact is a whole number. And if we were to graph whole numbers, we would do it just like I did for the counting numbers. We would only include 0 in that count this time, and that's why you see a dot above the 0. Integers are the numbers that include all the whole numbers and the opposites. So in this case, if we wanted to list integers, we'd have to list not only 1 but the opposite of 1, not only 2 but the opposite of 2, not only 3 but the opposite of 3, and of course that would go on as far as we could, and we would signify that by having the dot once again over the number. Remember, those numbers in between, all this stuff in between, all this space, there are numbers there, but they are not integers, and they are not counting numbers, and they are not whole numbers. Okay. Then we get into the idea of a rational number. The family of rational numbers includes all numbers that can be written as a ratio. Okay, so rational numbers are all numbers that can be written as a ratio. So things like 4 1/5, 4.25, 1.73. All those numbers are rational numbers. 1/3, 2/4, 5/6. These are all rational numbers. They're all ratio numbers. They're all going to make fractions. They're all these little numbers in between the whole numbers, in between the counting numbers, in between the integers. Everybody have a pretty good grasp of that? Are we okay with that? So on page 594, if we're given this question, and we are given this question as example problem number 1, and we have, let me just put some numbers on here. Julie and Ann, if you guys continue to talk and distract each other, you can get outside the classroom and do it out there where I don't have to see it. Are we clear on that? We good on that, right? Next time, just get up and leave. If you feel the urge to talk, by all means, feel free to leave the class and learn this material some other way. Don't feel obligated to stay here and annoy me and disturb your classmates. The next time it won't be an invitation, it'll be a command. I'll expect you to leave. I'll ask you to leave. Okay, so continuing on with this example. If anybody thinks that's funny, you can go too. We want to graph the integers that are less than 4. Graphing the integers that are less than 4. So integers are what? What are integers? Anybody know? Yep, Emma? The opposite. So it's any of the whole numbers or counting numbers and the opposite, right? So if we had, remember, it's important to know that an integer is, the 0 is included as an integer, okay? Even though it's not the counting number, it's a whole number. So it is included. So for example, if it says graph the integers that are less than 4, up here on that graph, I'm going to graph, what's my first integer that's less than 4? London? 3. Okay? And then of course, if 3 is, so negative 3 is also, right? And then 2 would be, so the negative 2 would be, the 1 would be, the negative 1 would be, and of course 0 would be as well. Let me see, where are we? Okay, and we can actually, if it's asking for numbers that are less than 4, then we can continue on by putting dots over the negative 4, and we can put a dot over the negative 5, and then what we have to make sure we do is we put that arrow going to the left, that negative direction, and that's signifying that all numbers, because we're asking for numbers that are integers that are less than 4, it doesn't stop at negative 5, does it? That line goes on for how long? Forever. So that arrow, that red arrow says that in fact that we are telling the reader that these numbers don't stop at negative 5. They go on forever. That's as far as our line went. London? That is correct. Yeah. Yeah, you don't stop, because if there's a number, like there's a 4 here, so if I put a dot, because that is an integer, right? That's a counting number who has an opposite of negative 4. But if I didn't put that mark there at the negative 5, then what am I telling the reader? Right. They're asking for numbers that are less than 4 or less than 5. So if the question was for numbers that are less than 5, 4 would be the first one, and then any number to the left thereafter would be less than 5, right? So we wouldn't stop at negative 4. We're not just going to match the 4 here. We would in fact put that dot over at negative 5, and if we had a negative 6 here, we'd put a dot over that as well. And that goes on for eternity, for infinity. Even if there wasn't? The question was, and I didn't write it down, I read it to you, the question was graph the integers that are less than 4. Okay? So obviously we wouldn't graph 4, but we would graph 3, correct? That's an integer less than 4. What are these numbers in between 3 and 4? What are they called? They're like ratio numbers. What do we call them? Rational numbers. So none of those numbers would count, right? So it's asking for a number that is less than 4. If it said integers that are less than or equal to, it'd be a different story. We'd include the 4, right? But it's asking for numbers that are integers that are less than 4. So we want all the whole numbers, all the counting numbers, and all their opposites less than 4. And it wouldn't stop at 4, because wouldn't minus 5 be less than 4? Wouldn't minus 6 be less than 4? Now minus 7 is over here somewhere. We don't graph it, but is it less than 4? And minus 8 and minus 9, that's out here in the clouds somewhere. But this red arrow is saying that it's actually going to pierce through all those numbers as well. It just keeps on going on forever and ever and ever, and it just will not stop. You, okay. Yes. Yes. Okay. Do I need to be here? You don't need to be here. But the room needs to be prepared. Okay. Thank you. Yeah, Emma? No, I'm sorry, Mrs. Nelson? Do they want the chairs up or do they want the chairs down? Okay. Great. Thank you. Sorry, Emma. Yeah. Yeah, don't do a line. If you do this, if you put this line here, then you're including what? All this stuff in between, right? And they are not integers, they're rational numbers. So you don't want to include those by putting that line over there. Got it? That makes sense, Amanda? Yeah. Yeah. But and you go as far, and if it's asking for less than, you're going all the way to the left forever. Unless it were to say the numbers that are less than 5, greater than something, or if it gives you a boundary, right? But there's no boundary here. It's simply asking for less than 5. So that anything, or 4, whatever was the actual question. So anything less than 4 is just going to go on forever and ever and ever. So then this takes us to a true or false question. Are all whole numbers are integers? All whole numbers are integers, true or false? All whole numbers are integers. They all have opposites, that's right. So how about this one? All rational numbers are integers. False. Good. Actually, all integers are rational numbers because you can put that number over 1. You can put it over 1. You can make an integer a rational number by putting it over 1. It's like -7. It's an integer, right? You put it over 1, it's also a rational number. It's a ratio. Hopefully they won't ask you questions like that. Okay, guys, there's just 2 or 3 problems in the practice set, and I think these are easy enough that you can do them without having to do the practice set in class. I really want to move to 87 since we lost a day, and try to pick it up if we can by talking about this lesson on multiplying algebraic terms. Now, listen, this is where you have to start focusing from here on out. This class gets a little bit harder, and there's just more expectation. You're really going to have to start grasping some of these concepts. You'll know that a few lessons ago, maybe in lesson 84, whenever it was, we actually had a problem like 3x plus 2x, and we said it was 5x, and we were also combining like terms. Remember when we were combining like terms? We said, I think we said something like if you have 3x plus 2y plus 1x equals what? And we combined the like terms. We said the 3x and the 1x are the same, so that's going to give us 4x, and then we have a plus 2y left over, and that was our answer, right? You remember that? Okay, same kind of concept, but there's a little bit of a twist, because now we're multiplying the algebraic terms, and things are a little bit different when we multiply. So let me scroll this up here for a minute, and this is where you're going to want to take good notes. Either follow along in your book. I mean, whatever works for you. Look at the screen. This will be on the blog, so if you're confused, you can also watch it tonight. But here is our problem that we're going to have, and it's going to be vastly different from the ones that we're used to. We have minus 3x squared y times, because we have it in parentheses, 2x times negative 4xy. This is why it's important to understand these negatives and positives and multiplying and this and that, Brooke. Pardon me? Oh, good. Oh, good. Okay. All right. So yeah, we're now this is a case where you can actually group the terms that aren't alike because we're multiplying them. So things are a little bit different. Okay. Things are a little bit different when we do this. Um, Basically, the way your book, I'll show you the long version, the way your book is doing. If you take the first problem here, the 3x squared y, the negative 3x squared y, what it's basically saying is we have negative 3, and then remember these are all together, so we're multiplying all this stuff, right? There's no addition or subtraction sign, so whenever numbers are next to each other, it's understood we multiply them, correct? So we have negative 3, and then we're multiplying that by x and by x, because we have x squared, and also multiplying that by y, okay? And then we're multiplying that by the positive 2, because it's a 2 there, and that's being multiplied by x, okay? And then we're multiplying that by the negative 4 times the x times the y. Okay, that's the longhand version of what this here is. So what all this stuff here is that I'm circling, this is the longhand version of it being written down in a more concise, compact kind of way. Does that make sense to everybody? Oh, okay. Well, this is yeah. Think of it this way. This here, what I'm underlying now, is the shorthand version for all this. You see how we took 3x squared y, and in longhand version it's negative 3 times x times y. It's the same thing as saying minus 3x squared y. 2x is the same thing as saying 2 times x. Negative 4xy is the same thing as saying negative 4 times x times y. Because you understand that in between these variables, there's really little multiplication signs, but we don't show them. They're understood to be there, right? See, I'm putting them in there now, but you know that they're kind of understood. They're just known to be there. You're supposed to know that we multiply all those things together, Amanda. Okay. Well, this is why you have to know, and this is what we're here for. You know that when you have two variables together, we're still multiplying them. Okay, they're still multiplied. xy is not a term xy. X has a value, and y has a value. So they're handled separately. Okay, makes sense? Are we okay with that? All right. So the way we do this is now we can collect. Your book shows you about collecting all the like terms, and so we have this negative 3 we're collecting. We have a positive 2 that we're collecting. We have a minus 4 that we're collecting. Those are terms that are alike. And then we also have the x's. We have an x here, an x here, takes care of those two x's. We have an x here, so we'll add it. We have an x here, so we'll add it. Okay. By the way, we added the 3, the 2, and the 4 so we can get rid of them. And the only thing we're left with is a y here we'll put down and a y here that we'll put down. Okay? That's what we've accumulated. So now when we add everything up, well, when we multiply everything up actually, when we multiply everything up, we have negative 3 times a positive 2 is what? It's going to give us negative 6 times a negative 4, which is going to give us what? It's going to give us a positive 24 because a negative times a negative is a positive. And then what do we have here? How many x's do we have? So we have x to the 4th. How many y's do we have? Y to the 2nd. Okay, we're adding our x's and our y's, our variables, and that becomes our exponent or the superscript over the variable. Do we all see that? Does that kind of make sense? Anybody completely lost or lost even a little bit? Tanisha, where you lost that, kid? How do I get from here all the way to here? Oh, from here, from like this point to this point? Okay, well I've just rewritten in longhand what they told me up here. You see where I have the -3, so I bring it down? How many x's do I have up here? Okay, how many do I have here? I put them down that way. How many y's do I have? I brought it down. Okay, what do I have over here? I have a 2. I brought it down. How many x's do I have? I brought it down. What do I have over here? How many constants do I have? Just one. Happens to have a name. The name is -4, so I brought it down. How many x's are over here? I brought it down. How many y's? I just brought it down. Okay? I brought everything down. The only way this looks a little bit longer is because I have x squared. So I have to have x. I have two x's, so I have x and I have x. And I broke this x squared up into x times x, because x times x is x squared. Does that make sense? So this is just like a longhand version of what this is up here. Kind of like scientific notation. Kind of like scientific notation. Emma? Yeah. Never keep them together. Because x has its own value and y is going to have its own value. Christine? Yeah, that's x to the fourth and y to the second. Okay, you're welcome, London. How do you like what? How do I know when I'm here? Well, when I've taken this original problem and I've broken it down into its longhand version, then I'm pretty much done. I mean, I didn't have to go to this step here you guys are looking at. Let me change the color. This step right here, I didn't have to. Your book did that. I didn't. I wouldn't necessarily do that. And honestly, I wouldn't even do this step. Quite honestly, I mean, I can. I mean, I don't know if this will clear things up or make things more confusing. But let me just show you, and then you can decide if you like it or not. I'm going to take that problem over again, and we're going to have minus 3x squared y, and we're multiplying that by 2x, and we're going to multiply that by minus 4xy. Okay. The way I would take this problem myself personally is I would take all my constants, my minus 3, my 2, and my minus 4. You know what constants are, right? Everybody know what a constant is? It's a number that has a value. It's not a variable. We know a -3 is always going to be a -3. It's never going to be anything else but a -3. A constant. We've assigned it a value. It's got the value of -3. A 2 here could never be a 4. Can never have the value of a 4. An x can have a value of anything, right? Depends on the problem. X can be 2 for one problem. X can be 9 for another problem. Do you understand why? Do you understand why? Yeah, watch. If I say 3 plus x equals 5, what's the value of x? 2. What if I say 3 plus x equals 9? What's the value of x? See how it changed? This 3 is always worth 3. You can't say that 3 is worth 2. It's a constant value. It never changes. The variables always change. Or they can always change. Doesn't mean they have to, but they have potential to change because they're variable. But what I do is I take my constants, those things that can't change, and I simply multiply them to get them out of the way. -3 times 2 is -6. Would you agree? -6 times -4 is a positive 24. So I have my 24. Then I take my x's. How many x's do I have? I have 2 x's here. I have 1 there, that makes 3. I have 1 there, that makes 4. So I have x to the 4th. How many y's do I have? There's 1 there and there's 1 there. So I have 2 of them. Now you see what I did? Look at it. I cut out all of this. All this I cut out just by simply taking my problem here and multiplying the constants and adding the variables. That's pretty simple, isn't it? So you can do it either way, whatever way works best for you. We're going to do another one. Is anybody like still completely foggy about this, or is the fog starting to lift a little bit? Are we okay? Okay, good. Starting to lift? Good. All right. Well, let's look at another one here and see how we're doing. Um, we got minus 2ab, and we're going to times that by a squared b, and we're timesing that by 3b cubed, or 3b to the third. Now we can do this one of two ways. We can do the long version, right? I can take my constant, my minus 2. I can bring my a down because I have one of them times the other b, right? And then I can multiply that by, how many a's do I have here? So by a, and then I have a b. I bring that down, right? And then I have my 3, so I want to separate that. And then how many b's do I have? That's a 3. That's a 3. I mean, that's a 3 right here. I have 3 right here. Okay, I'm bringing it all down. So now I want to multiply my constants. I only have 2, negative 2 and positive 3. What's my answer? Negative 6. And then I'm going to count my a's. How many a's do I have? 1, 2, 3. And then how many b's do I have? 1, 2, 3, 4, 5. That's my answer. 6a to the third, b to the fifth. London? Okay. It'll just say simplify. Yeah. Yeah. Okay. That makes sense, guys? Not so bad, right? Now, could I have done this a shorthand version? I could have, right? I could have taken my constants, my negative 2 and my 3. I have to multiply them because we have all these parentheses. It's all multiplication here. And I would have had negative 6. And then I can take my a, my 2 a's, and that gives me 3 a's. So I put a to the third. And I count my b's. There's 1, there's 2, and there's 3, 4, 5. B to the fifth. Joy? It's 3 b's. It has a value of 3 b's. Just 2 a's. It's a times a. Are we okay with that, guys? No? Who said no? Anybody say no? Okay. Just wanted to make sure. The only other thing your book talks to you about is going to give us an example. Yes, it is. It talks to you about multiplying exponents to find a power of a power. So now this is where the waters might start to get a little muddy again, or the fog might start to settle back down. If we have something like x to the a to the b power, then our answer is going to be xab. Huh? What? Watch. Let me try. Let's put it. Listen. Variables always confuse me. Let's do what the book does, and let's put it in terms of some numbers and see how much easier it is. Let's say we have 3xy squared. Yes.
Hey, can I see Tanisha?
Sure.
Thanks.
You're welcome. All right, guys. So look at. Stay focused. We only have 7 minutes. We have 3xy, and it's squared. Okay. So what does that mean? That means we have 3xy times 3xy. That's what it means, right? That's what it means. So don't let that confuse you. So when we do our answer, what are we doing? We're taking 3 times 3 is 9, right? We're taking x squared and we're taking y squared. Okay? The same thing if we would have taken the 2 and taken 3 and squared it and added 2 x's and 2 y's. Okay? Do you see that? Is that okay? Let me lift this up and do another one. Let's look at this one here. Let's say we have 3x squared. That looks like a y. X squared, y to the third, and that's all squared. Okay? That's like saying that's going to be equal to having 3 squared times x squared times what? Well, it's actually x. Hold on. I put a 3 in there. Wait a minute. Hang on. Oh, I did that right. Wait a minute. Getting ahead of myself here. 3 squared. Then it's x squared. What are you guys looking at? Oh. Stop looking at that. Stop looking at that, please. Guys, stop looking at that. Stop. We're at the hardest section of today's lesson, and now we're going to start looking around the room.